After 50 years of non-stop flight, Voyager 1 has only just stepped beyond the doorstep of our solar system, still hovering at the edge of our cosmic neighborhood. Even at nearly 38,000 miles per hour, it would take centuries just to skim the inner rim of the Oort cloud, and tens of thousands of years to drift near another star. But if this tiny, aging spacecraft keeps slipping through the dark for millions, even billions of years, how far can Voyager 1 truly go? Voyager 1 has left the planets behind, but it hasn't left our questions. As its weak signal crawls back to Earth, something inside the data begins to slip. Tiny timing errors, subtle shifts in its position, numbers that should align, don't. In control rooms and midnight offices, astronomers rerun the models. The same result. Voyager 1 is not exactly where our physics says it should be. The difference is small, but at interstellar scales, small becomes terrifying. If our most trusted equations fail out here, what else are they wrong about? Because if this lone probe can drift beyond the map of our known laws, what does that mean for the future of our solar system and everything orbiting inside it? Voyager 1 has left the planets behind. Its signal is crawling home through a sea of charged particles and interstellar plasma that should, by all our calculations, be quiet and predictable. But the farther it falls into that dark ocean, the more data it sends back begins to strain against the rules that were supposed to define its journey. Launched on September 5, 1977, from Cape Canaveral, Voyager 1 was never meant to be a ghost ship at the edge of the Sun's influence. Its first task was simple by cosmic standards: a grand tour of Jupiter and Saturn, using gravity assists to slingshot it out of the inner solar system. In 1979, it plunged past Jupiter at about 17 kilometers per second, mapping storms, thin rings, and volcanic moons. A year later, it threaded Saturn's rings and bent its trajectory sharply upward, out of the plane of the planets, onto a one-way path into the dark. From that moment, Voyager 1 became less of a mission and more a question fired into deep space. Its instruments, magnetometers, cosmic ray detectors, plasma wave sensors, and imaging systems, began to track the invisible structure of the Sun's outer atmosphere. At first, the readings fit the models. Solar wind thinning with distance. The Sun's magnetic field is stretching, charged particles fading into background noise. For decades, every spike, dip, and fluctuation could be folded neatly back into the equations. Then, it reached the edge. Around 2012, at roughly 121 astronomical units from the Sun, more than 18 billion kilometers out, Voyager 1 crossed the heliopause, the boundary where the Sun's charged particles give way to the denser plasma of interstellar space. The transition was not clean. Instruments registered a density jump more than 40 times higher than the outer heliosphere, a pressure wall where solar particles slowed and interstellar plasma pressed back. Inside NASA labs, that cosmic purgatory was both expected and unsettling. A turbulent frontier where even small mismatches between models and measurements hinted at hidden forces. The data stream that carries these measurements is thin but relentless, about 160 bits per second at best, captured for a few hours each day by the Deep Space Network's giant radio dishes in California, Spain, and Australia. Every bit encodes the behavior of fields and particles in a region no human instrument had ever touched before. Before Voyager 1 crossed that boundary, the expectation was that beyond the heliopause, conditions would settle into a relatively uniform interstellar medium. Steady plasma density, magnetic fields aligned with the local galactic field, and particles moving in smooth, predictable distributions. That is not what Voyager 1 has found. Instead of a calm, featureless sea, its instruments have reported sudden bursts of plasma oscillations, sharp changes in particle density, and unexpected twists in magnetic field direction. Signatures of a boundary region far more dynamic than any simple model allowed. In some intervals, the plasma density surges well above the smooth background values, as if Voyager 1 is brushing through invisible structures, waves, or filaments woven into the interstellar medium. For mission scientists trained on decades of clean planetary trajectories, these are not just curiosities. They are warnings that space between the stars is not the stable vacuum once imagined. The centerpiece of this unease is simple and brutal. At interstellar scales, even tiny deviations matter. In the Pioneer missions, a minuscule, unexplained acceleration of around 8.74 times 10 to the minus 10 meters per second squared, now largely attributed to thermal recoil, was enough to move the spacecraft hundreds of kilometers from their predicted positions over a single year. Voyager 1 operates in a similar regime of precision, where a barely measurable force, an unmodeled pressure, or a subtle magnetic drag can, over decades, stretch into vast discrepancies between where our equations say it is and where reality chooses to put it. If any persistent anomaly emerges in Voyager 1's trajectory, a drift that cannot be blamed on thruster leaks, thermal radiation, or tracking noise, it would strike at the heart of gravitational modeling beyond the planets. Orbital mechanics that keep distant spacecraft on course are built on the same laws that describe how stars orbit the galactic center and how dark matter is inferred from their motion. A crack at the edge of the heliosphere would echo up the ladder, forcing physicists to ask whether the force shaping Voyager 1's path also whispers through the orbits of distant stars, the spin of galaxies, or the slow breathing of galaxy clusters. Each new year adds more samples of interstellar plasma density, more glimpses of magnetic structures, more hints of discontinuities and shocks that do not line up cleanly with any single model. Instruments designed in the 1970s are now probing physics that theory has only just begun to catch up to, and with every contradictory reading, the quiet pressure grows. Perhaps the neat picture of a smooth heliopause and a placid interstellar medium was never true. Because as Voyager 1 drifts farther from the Sun, deeper into a region no other machine has entered, the data only gets stranger. And somewhere beyond the noise and the gaps, a second, darker question begins to form. If this is what the universe looks like just outside our own solar system, what will we find when the next generation of probes pushes even farther into the galactic night? And then, just as the data seems ready to fade into background noise, something new appears. Not in the plasma, not in the magnetic field, in the timing. A tiny, repeating delay slips into Voyager 1's signal. Then a second delay, offset by a fraction of a second. Engineers blame aging hardware, software, ground systems. They test everything. The pattern remains. The signal seems to bend, as if it has taken more than one path to reach Earth. Cross-checks with the Deep Space Network show a deeper problem. When they compare Voyager 1's radio arrival times with the probe's last known trajectory, the light travel distance no longer matches the position by a few kilometers, then tens, then more. As if the space between us and Voyager 1 is stretching, warping or folding in ways no current model predicts. Voyager 1 cannot decode that truth. It can only feel it. As drifting changes in plasma density, as subtle warps in the path its radio waves must cross, as quiet deviations that slip between our equations. A single pale signal, fading through static, still has the power to redraw the edge of the known universe. One small probe, launched by hands that had never seen beyond the planets, is now testing the limits of what those same minds believed was possible. If the space just outside our solar system already bends our rules this easily, what will the next generation of explorers find when they chase Voyager 1 into the deeper dark? Subscribe for more cosmic documentaries.